Boyle's law is a scientific gas law. Boyle's law states that with constant temperature, pressure and volume will be inversely proportional. And so let's go over some standard gas rules first so we can understand Boyle's law better. Gases have no definite shape. Gas molecules constantly move around, excluding 0 Kelvin. So this means that gas molecules will always float around until they're liquids, of course, but gases are just made of free-flowing molecules, and gases will always spread out to fill its container. So here's the variables in Boyle's law. P stands for pressure, obviously, which is the amount of time the molecules will hit the wall of its container. V stands for volume, which is basically how big the container is or how much room the gas has to move. N stands for moles. T stands for temperature, so in kelvins. Temperature. And R is just always a constant. R is L times atomic mass, or atomic pressure over moles times Kelvin. And this standardly equals 0.08206. And this is just a standard gas law. This will always be that number. So N, R, T are all constants in Boyle's law. Temperature always needs to remain constant, because if the temperature changed, then the rate at which the molecules would change, disrupting Boyle's law, and we'll see why that happens later. Also, moles needs to remain a constant because if somehow in the process of the experiment the amount of moles were to change, then that could increase or decrease the pressure, because there'd be more molecules hitting the wall's container, so just also moles must remain a constant. Okay, so here's a real-world example that'll help explain pressure and volume more. So in balloon A, we have a balloon with a smaller volume, which means, because of Boyle's law, that the pressure will be more. In balloon B, we have a balloon with a higher volume. That means the pressure will be less. And this is because since the temperature is constant, with constant moles, there'll be the same amount of molecules moving at the same rate. In balloon A, they're moving at the same rate, but since they have a tinier space to move in, the pressure will be more, because pressure is how much or how often molecules hit the walls of its container. And so in balloon B, this is the inverse. Since the volume is bigger, there'll be more space for the molecules to fly around in, meaning that they'll hit the walls less. Boyle's law is based off of physicist Robert Boyle, who discovered and published the law in 1662. Robert Boyle was a philosopher, a chemist, a physicist, and a writer. Overall, he was a pretty smart guy, paid attention in class. So this is like an example of how this isn't how the experiment he used exactly, but this is just to put in easier terms. So Robert Boyle used this simple experiment right here. He had a beaker full of gas in a box of water, basically, and it was in water so he could regulate and keep the temperature constant. And then the beaker had a piston on top, and what he would do is he'd lower the piston, decreasing the volume, and then he'd measure the pressure, and then he'd raise the piston, increasing the volume, measuring the pressure, and he found out that his theory was correct. When he decreased the volume at constant temperature, the pressure increased, and vice versa. When he increased the volume, the pressure decreased. So this successful experiment proved that at constant temperature, pressure will be an inverse of volume and vice versa. So here we're going to show you a real-life experiment where we put a balloon in a vacuum, and we're going to decrease the pressure, and we're going to see what happens to the volume of the balloon.
What's happening here is the vacuum is pulling out all the air in the container, which is applying pressure on the balloon, allowing the volume to expand. Not only does this decrease the pressure inside the container, it increases the volume of the balloon, decreasing the pressure inside the balloon. This proves Boyle's law. It's scientific laws like these that help us chemists understand how scientific properties actually apply in the real world. Thanks, Robert Boyle.